Scott Quillinan and Fred McLaughlin are going to be talking with us about the science of carbon capture, utilization and storage, Wyoming case studies, and the Wyoming CarbonSAFE project. Scott is a Wyoming native, a licensed professional geologist, and director of research for the School of Energy Resources at UW. Quillinan manages the SER research, including several Department of Energy funded projects, including our CarbonSAFE project out here at Dry Fork Station. Scott's research focuses on the interconnections between energy resource production and groundwater resources. Over the years, he has worked with energy and water ground challenges associated with the production of coal bed methane, oil and gas, hydraulic fracturing, and CO2 sequestration. Scott was born and raised in Evanston, Wyoming, and attended the University of Wyoming. By the way, how many UW graduates do we have? All right, cool. That's right. Well, you know, the world needs more cowboys, and I'd say the world here in Gillette's got quite a few cowboys in this room, so that's terrific. I just have to say, in his personal time, Scott is an avid outdoorsman, loves everything and anything to do with bicycles and a pair of skis, and he's a huge Wyoming cowboy fan. So I'm also going to take a moment, though, before he steps up here, to introduce Fred a little bit more thoroughly. Fred McLaughlin has a PhD in geology. He's a professional geologist, and he is senior research scientist at the Center for Economic Geology Research at the School of Energy Resources. He's a 3-time alumni of Wyoming, and he loves the geology and geophysics department, so he stayed around for every degree that they offer, it looks like. His areas of research include the isotopic evolution of groundwater and rocks, basinal diagenesis, geochemistry and petrology, natural gas and coal, and geologic reservoir characterization. He's going to tell you what that means. To date, McLaughlin has played a technical role in all of Wyoming's major CCUS research projects. So we're going to start off with Scott, and then we're going to go to Fred. Please help me welcome Scott.
All right, thank you. All right, thank you. It's a pleasure to be here in Gillette. It's always a pleasure to come up to Gillette. Like Gene said, I was born and raised in Wyoming, and it just feels good to get out and visit some of the towns around the state and participate in research projects like this. So I'm not a lawyer, I am a geologist. So Kip, you're a hard act to follow. Kip is just a wealth of information. He's so articulate, he's so fun to have in the office, and Wyoming's lucky to have him. Really, the School of Energy Resources is lucky to have you too, Kip. So thanks for starting us out. But I'm going to bring us back to Gillette. I'm going to start talking about what the CarbonSAFE project is surrounding Dry Fork Station. So as we all know, most of the carbon capture and storage work is funded by the Department of Energy. Carbon storage is no different. CarbonSAFE is the flagship Department of Energy carbon capture and storage program right now. I got to get a little closer to the computer here. But these projects are developed to identify the key research gaps to take us to commercialization for carbon capture and storage. And they hope to get there through a 4-phase program. We've already gone through phase 1. We're in phase 2 now, which is storage complex feasibility. If we get through phase 2, we'll be competing for a phase 3 project and a phase 4 project. A phase 4 project may be permitting construction and a full commercial project here in 2025. So what about carbon capture? This project does not deal with carbon capture. This is only about looking at the rocks, looking at the storage reservoirs below Dry Fork Station to see if we can put CO2 in the ground safely and permanently. Now there is another DOE program that deals with carbon capture. It's on a parallel path to CarbonSAFE. So that path at some point is going to merge with the CarbonSAFE program somewhere around 2025, and those will form a carbon capture and storage project. 3 of the 2 projects that are out there competing in that other phase for carbon capture are also competing for their phase 2 project. 2 of those 3 may be at the Integrated Test Center here in the next round. So this is what the CarbonSAFE program looked like when it first came out. There was 13 phase 1 projects funded. It's hard to see the screen here. And 3 phase 2. So that projects that could demonstrate that they could go straight into a phase 2, could apply straight for phase 2 funding. The University of Wyoming won 2 phase 1 projects, one at Dry Fork Station here in Gillette, and the second at the Jim Bridger Power Plant in southwest Wyoming at the Rock Springs Uplift. So we went through phase 1, and then we put in applications, and DOE down selected those projects down to 6. So now there's 3 phase 2 projects that were funded in the first round, and there's 3 more phase 2 projects that made it through this second round. We're one of them. The project at the Rock Springs Uplift didn't make it to the next phase, but the Dry Fork Station project did. Those 3 projects in the middle, in the Midwest, those guys they realized that they weren't able to compete on their own, so they got together with their neighbors and formed one project in the Midwest. There's another project that formed with the Decatur project over in Illinois Basin. So we've got a North Dakota CarbonSAFE, we've got 2 CarbonSAFE projects in the Illinois Basin, there's Kemper County down in Mississippi, the Midwest project, and then us up here at Dry Fork Station. So who's our team? We're teamed up with Basin Electric, we're teamed up with the Department of Energy. Advanced Resources International is a large consulting company that have been doing this for a really long time. The EERC, the Energy and Environmental Research Center in the University of North Dakota, is also a major player in the carbon capture and storage network, so we're lucky to have them on the team. The Integrated Test Center, of course, is on the team. We're teamed up with Schlumberger and Core Labs, CMG. They've all made large software and cost share donations to the project. The Enhanced Oil Recovery Institute. There's a lot of names on there I haven't mentioned, but maybe let me mention KKR. KKR holds $1 billion hedge fund investment in energy, transportation, and development. So you might say, well, why is KKR interested in a project like this? Well, KKR also owns and finances enhanced oil recovery projects here in the state of Wyoming. So we've got a robust team here, and we're very thankful to our hosts, Basin Electric and Dry Fork Station, that they allow us to use their plant as a proxy for our research project. So here we are at Dry Fork Station. It's the newest coal-fired power plant that's been built in the U.S. It's the most efficient one that's running. I'm sure everybody in this room has driven by it or been out for a visit. But it may be the last one that's ever built. If we don't figure out carbon capture and storage, if we don't figure out a way to decrease carbon emissions from coal-fired power plants, there may never be another coal-fired power plant built. Now, attached to the Dry Fork Station is the Wyoming Integrated Test Center. The state of Wyoming's put in $15 million. They were able to find another $5 million from private investment. And the Integrated Test Center is hosting the Carbon X Prize and Kawasaki Heavy Industries out of Japan. So these teams are competing. To develop carbon capture and utilization technologies. I'm sure everybody in this room knows, but if you haven't been out to the Integrated Test Center, this is what it looks like. So the Integrated Test Center is made up of small test bays and large test bays. On the top there are the small test bays. That's where the pipe comes out of the fence from Dry Fork Station. This is where the skid-loaded pilot technologies will be able to bring in and bolt onto those pipes and test their technologies. Now, on the bottom, the large test bays, that's where Kawasaki Heavy Industries and J-Coal will be testing their carbon capture technologies. There's also a second large test bay that's in development now. So if you look at that yellow square on the map directly south of Dry Fork Station, that's the location of the CarbonSAFE project. It's about a quarter mile south of Dry Fork Station and a stone's throw away from the Integrated Test Center. So we're lucky to have the newest coal-fired power plant, the Integrated Test Center, and now a site for carbon storage. So why is this project attracting so much, not only statewide attention, national attention, but international attention? It's because it just has so many different low-carbon technologies that are being tested. So listed there are all the teams, the international teams that are competing for the Carbon X Prize. We have the CarbonSAFE project that's going on. So if we step out from Dry Fork Station, what we see here is a 50 diameter circle surrounding Dry Fork Station. All those blue and green polygons, those are oil and gas fields that are nearing the end of their economic life for primary recovery. They can still go a long way in tertiary, and soon they'll be looking for a source of CO2 to continue producing oil and gas. Now off to the side, there's a red line there. That's a CO2 pipeline. It's a 20-inch line. It's currently running under capacity, so there's room to put CO2 in that line and take it out to market. Maybe to Bell Creek, maybe someday that line will go all the way to the Bakken. So if we step out again, this is why Wyoming is the place to do this. That 20-inch CO2 pipeline runs across the entire state. On that map, you'll see circles, gray circles there. Those are the anthropogenic sources that are point sources that are reported to the EPA. Down there in southwest Wyoming, my own stomping grounds, 60% of the CO2 emissions emitted in Wyoming are at the start of that pipeline. About 30% of the rest of the reported CO2 emissions come from the Powder River Basin next to that pipeline. So Wyoming could be one state where 70 to 80% of its anthropogenic emissions, if they could capture it and get into that line, could be utilized. I think this is the only place in the world it could happen. Every time we get one of these DOE projects, we're able to just kind of put that next piece together. So the pieces are really coming together. Now along that line, you'll see some blue triangles. Those are the active enhanced oil recovery operations going on today. The black triangles on that map, those are the next top 50 prospects. So there's a lot of potential for CO2 EOR in the state of Wyoming. On that map, there's dotted lines. This is a project that was put on by Governor Mead's office. These are pipeline right-of-ways. So if and when additional CO2 becomes available, building the pipelines out to the additional fields will be just that much easier. That's why all the eyes are on Wyoming. All the pieces are here, we just need to start putting them together. So what is the feasibility study? So every time I do one of these talks, these are the three big questions I get about carbon storage. One, is there enough space in the subsurface to put commercial quantities of CO2? Fair question. If we put it down there, can we keep it there safely and permanently? And three, what are the risks? I think during our feasibility study, we'll ask a lot of questions, we'll cover a lot of technical gaps, but I think if you back out, you can put them into those three buckets. So I'll talk a little bit about those three buckets here for the next few minutes, and I'll pass it on to Fred, who will give you the real technical details on the project. So is there enough pore space to put commercial quantities of CO2? We need to identify a storage tank down in the subsurface that we can put CO2 into. Now on the left there, that's our stratigraphic column. So beneath your feet, you're actually standing on the Fort Union Formation today. The Fort Union Formation, everybody knows that that's where the coal is mined from. It outcrops east of town, south of town, that's where the mines are. If you go down from the Fort Union Formation, you see the Lance Formation and the Fox Hills Formation. The Fox Hills Formation is your lowest USDW, United States Drinking Water Aquifer. So that's at the lowest point that you could drill a well below your feet and still hit fresh water. In the pink there's a nice conglomeration of shales. I call it a super seal. My geology friends laugh at me because a super seal is not a geologic term, but that's a super seal. We've got all these different shales that are put together that forms a major hydrogeologic divide across the entire Powder River Basin. So the fluids above it, our drinking water, are separated completely from the fluids below it where we're mining oil and gas. If you go all the way to the bottom of that stratigraphic column, you'll see the Menalusa Formation. This is our primary target that we're looking at for Dry Fork Station. The middle column, that's an example of a geophysical well log. We'll be collecting a lot of those in this next phase of study. But you can see the nice color-coded yellow pieces. Those are the sandstones that we'll be looking to target. So just to give you a sense of scale of how big those rocks really are, there's some nice, beautiful outcrops in the Menalusa. You've probably seen these if you've driven just over the South Dakota border on your way to Mount Rushmore. That's what the Menalusa looks like. We'll be targeting those sandstone intervals interbedded in between the dolomites there. So we can't just drill a well and start putting CO2 down. We have to have a really nice reservoir rock. It has to have porosity, it has to have permeability. One thing we'll be pulling out of the hole, out of the well, so that we can test for porosity and permeability is core. So on the picture on the left, what you see is an example of core. It'll come out of the hole about a 4-inch diameter. If we zoom in on that, you can start to see that in between the sand grains, you've got this blue space. If we zoom in a little bit more, the scale on the top of that is about 500 nanometers. But if you zoom in, you can start to see where the pore space lives in the rock. That's what we're exploring for in phase 2. We're going to drill a well so we can look for pore space. Once we understand the pore space, then we can start to look at rock volumes across the study area. We can start to calculate how much CO2 we can put in. So we also need to know if we put it in, will it stay there? So as part of the feasibility study, we'll be looking at the seals. And on the very left there, you can see a picture of a seal on the top, and I'm comparing it to the reservoir picture on the bottom. So you can see the difference in permeability and porosity between a seal and a reservoir. Remember, we've got a super seal in the Powder River Basin that's 5,000 feet thick. So I use the analogy of you're pouring a cup of coffee. So you take your coffee cup, you pour coffee into that pore space in the middle of the mug. That ceramic is impermeable to fluid flow. It holds the fluid. That's what we're looking for in the Powder River Basin. We'll also be taking some seismic data, looking at 3D seismic, 2D, and 3D across the area. So we're looking for structural traps. So little wrinkles where a buoyant fluid like CO2 might be able to be stored and trapped. In the bottom, we'll also be looking for stratigraphic traps. So we'll be looking for those really tight seals over the reservoir rocks. So when you first put CO2 down into the reservoir, it's physically trapped through structural trapping, through stratigraphic trapping. As it sits there a little bit longer, the pores pull it into it like a sponge. That's called capillary trapping. So the capillaries, the pore spaces pull the CO2 into those, and that's another trapping mechanism. As it sits there longer, the CO2 begins to dissolve into the water. So then you get solubility trapping. As it sits there longer and more CO2 goes in, that fluid begins to precipitate out carbonate minerals. So then you're taking your CO2, which you put in as a gas, when you compressed it, put it down the hole, it's a fluid, eventually turns back into the rock and is trapped forever. So what about induced seismicity? We've all read in the news that in Texas, Oklahoma, Kansas, where they're extracting oil and gas produced water and re-injecting it, it causes earthquakes. This is a video. Let me see if it'll play. We don't have that problem in the Powder River Basin. We don't have that problem anywhere in Wyoming. In fact, you can look at the study by the Wyoming State Geological Survey that did a long study looking at earthquakes and looking at all the produced water records, or the injected water records, and comparing them. They weren't able to find any incidents where injected water in Wyoming had caused induced seismicity. However, that's something we need to look at for this project. We need to understand if you put CO2 in, pressurize those reservoirs, are we going to cause earthquakes? So we'll be building some very complex geomechanical models and looking at pressure management options to make sure that doesn't happen. That star in the middle, that's Dry Fork Station. These little squares are all wastewater injection wells that have been injecting fluid into the Meadowlusa in this area for 40 years. And there hasn't been a record of induced seismicity. So we'll take that into account, but we still need to make sure that as we go forward that we're really being careful here. So what if it leaks? So the question is, in Wyoming, are the aquifers able to take the water, or in Oklahoma, is it a high pressure incident? So it turns out, and it's very more complex than this, but a very simple answer is, in Oklahoma, for some of the very first incidents that happened, they were removing, make a geologic model here with my hands, they were removing fluids and oil and gas from one side of a fault, and they were re-injecting it on the other side of a fault. So if you remember back to high school physics and your little force vectors where you have a normal force, a gravity force, they were effectively relieving the normal force on this fault, taking the fluids out here, putting them in here, fault slipped. Now there's a lot of cases with that, but in the Powder River Basin we don't have structural faults that will be extracting on one and pressuring on the other. So there's a lot of cases, but that's what happened down there. So what if it leaks? If you were injecting in my backyard, that'd be the first question I had. What happens if it leaks? So remember, when you put CO2 in the subsurface, it's no longer a gas after 3,000 foot of depth. It's now a supercritical fluid. So it behaves like a fluid. So it's going to have Darcy flow. So it's not as simple as you have this big gas pocket in the subsurface. If you were to drill a well down and hit that and have a gas explosion, that's just not how it happens. It's a fluid under there. Now it's a buoyant fluid. It's less dense than water. So as we inject the CO2 down into the reservoir, it's going to fill up the reservoir, create a plume, and it's going to move up and hit against that top seal, right? So it's going to be forced against that ceiling. Now the seal is impermeable, but what if we weren't able to see every fault, every fracture, and this CO2 finds one of those and it starts moving up through this seal? Now let me pause and let's look at this geochemical equation. Now I'm going to ask you to go back to high school again and think about high school chemistry. When you react CO2 and water, it reduces the pH. Good. When you take CO2 back out of the system, it raises the pH back up, right? So in a system where we're pressurizing CO2, we're lowering the pH. If that CO2 were to leak, it's the same as taking it out. What happens is you start to precipitate carbonate minerals, and that's one of those fractures right there. If a CO2-rich fluid flows through, it begins to precipitate calcite, it heals itself. So if this CO2 pressed against the seal finds a fracture and starts moving it up, it's only temporary, it fills itself in. So what happens if that fracture does keep open and the CO2 goes up? In the Powder River Basin, we have 32 mappable coal seams that lie across the basin. Coal is a CO2 sponge. If CO2 gets into the coal seam, it absorbs to the surface of that coal and it sticks there. It has more of an affinity to coal than methane does. Everybody remembers the coal bed methane, where you drill the well, depressurize the coal seam, eventually the methane will come off the surface of the coal. CO2 sticks to the surface of the coal. No, the only way you could get it back out is if you drill the well in a coal seam, pump all the water out, pump all the methane out, and then the CO2 would desorb off of the surface of the coal. Fred, I'm getting to you, sorry. So the last point I want to make, what if CO2 leaks into a groundwater aquifer? There's the reaction right there. If you mix CO2 and water, you get a carbonic acid, H2CO3. That dissociates, you get a pH term, H, and HCO3, bicarbonate. That dissociates again, you get another pH term, and you precipitate a calcite. So exactly what happens is you put CO2 in, it lowers the pH of your aquifer, but then it dissolves a calcite mineral and it buffers it back up. So there's CO2 in almost every groundwater. Now it's more complex than that, and there's other things that could go wrong, but just having CO2 in a groundwater aquifer it's just part of the natural system. So let me end with this slide. I want to just show you conceptually what this looks like across the basin. This is a cross-section across the Powder River Basin. The scale on it is about 100 miles. Our project is going to be in the middle of the basin. There we'll be looking at those very lower level, I got a point. We'll be looking at these very lower stratigraphic levels here in the Menalusa. I want to show that these are completely disconnected through all these faults from the surface outcrop over here. Now the municipal drinking water supply for Gillette is the Madison. The wells are over here on the eastern side of the basin. The Madison is stratigraphically below the Menalusa. So remember, CO2 is a buoyant fluid, so it can't go down. It can't go down from the Menalusa to the Madison. That just can't happen. The other thing, as the Madison recharges over here, this water never makes it down into the basin because they're just disconnected. There's no connection between the recharge on the basin margin and the rocks that we're looking at in the deep basin. And here's Fred. Sorry, Fred, I took some of your time.
So I got the easy easy task tonight because I'm just going to talk about what we're going to do in our field operations for our CarbonSAFE Phase 2 project. And Jean introduced me. I appreciate that. Thank you very much. And she mentioned I've got 3 geology degrees from the University of Wyoming. So whereas Kip came out here based on a stack of statutes enacted by Cheyenne legislators, I came out here because there's mountains, judge us accordingly. So, so our field operations for this phase of the project are really straightforward and very simple. We're going to, 1, drill a research well to try to better determine the geology. We're going to collect subsurface data from that well, and we're going to acquire a 3D seismic survey regionally around that well so we can expand our knowledge from the well. Nowhere will we put CO2 in the ground during this phase of the project. This is a map of our field area. The yellow box there, it highlights where we're going to drill our well. That's the site. It's south of Dry Fork Station, about a mile. The red dots that surround that field area, those are existing wells there already. So we already have a wealth of knowledge about some of the subsurface around there. They're not all deep wells. A lot of them target the muddy, but that already, as geologists, gives us a great sense of understanding of some of those subsurface parameters that we're trying to look at. So this slide too, I want to introduce some of the work that's being done by our field crew, our work crew. So all the groundwork and all the civvies is going to be done by Western Fuels. They're one of our partners out there, and we're lucky to have them. So they know that piece of ground better than anybody. The field management is going to be handled by Carbon Geocycle. They're a Laramie company with Wyoming people. The engineer that works out there actually grew up in the Black Hills, and he cut his teeth drilling muddy wells in the Powder River Basin. Site access and a bunch of the oversight is going to be handled by Dry Fork Station. They'll have a million other jobs too, but that's as much as I could fit in the little paragraph box there. We have identified 2 Wyoming companies that will probably take care of the drilling. We have to do the due diligence on bidding and oversight. Same with services. And a geophysics company will also be handled by a company with regional Wyoming experience. This is a schematic of the drill pad as provided by Basin Electric. It was actually the laydown yard for Dry Fork Station. It's adequate size-wise to put 2 wells there if we wanted to. We're very lucky to have this spot. And this is kind of a projected timeline. It does say April 1st, but this is just an exercise of how long it would take to do the first phase, which is drilling. So our goal of drilling, of course, is to drill a deep stratigraphic test well, close to 10,000 feet. We'd core it, which we're very lucky to be able to do. That's an expensive component, typically, that doesn't get done in most oil and gas sites. So that's lucky for us because that's where we get our science from. We'll log it, and then the goal for this phase is actually to plug and abandon that well, remediate and close, and do all the reporting. The last field operation we'll do at the site after we close out the well site is a seismic acquisition. We can kind of start doing this sometime in the summer. The white checked box is kind of our area extent. The lines that crisscross the box are existing 2D seismic lines that we already have and we've already started to interpret. And what this does, again, we'll take what we know from one spot in the ground, just one well, and greatly expand that subsurface knowledge and reduce uncertainty with respect to the reservoirs and the seals we're trying to study. And these are some of the reservoirs that we'll be targeting during our drilling and exploration phase. So the youngest is the Muddy. It's a prolific oil producer. It's a fluvial system. That means it was laid down by rivers back in the day. It's Cretaceous. It's very heterogeneous because of it. You can imagine channel sands, channel bars running all across the basins from high mountains to the west back in the day. Same for the Lakota and Fall River system. Again, those are fluvial. The next formation we'll be studying the Lower Sundance. These are actually marine systems. We're laid down offshore, very homogeneous because of it. And then last but not least, as Scott mentioned, the Metaluna system, sorry. And that was actually really interesting. It's kind of analogous to what you would see in the near present-day Middle East. So you had massive sand dunes, very barren landscape with nearshore marine deposits. And these are paleogeographic maps, just to kind of show what these reservoirs look like when they were laid down back in the day. On the left, you have the fluvial systems. These are large, the Muddy and Lakota. They were laid down 100 million years ago, give or take, into systems that progressed to the north. And then on the right, you have what your Menalusa system might have looked like back in the day, massive Sahara-type sand dunes with shallow seas next door. So this is the interesting bit for geologists, is the fact that we get to get core. And we're going to get core all the way down from the Menalusa, and we're going to pull out sand grains that haven't seen the light of day for over 300 million years. So that's really kind of the esoteric and academic part for us. So that's the fun. So we have 4 targets. We have the Menalusa at the bottom, again, that lower Jurassic system, which has some decent sands, and then the Cretaceous sandstones I mentioned earlier that were fluvial river systems that were fairly complex. And as Scott mentioned, we can't just take geology and be done with it. We have to actually validate the feasibility. So really quickly, we're just going to walk through some of the stuff we hope to do. So the first data we hope to get back from the well is the core. And the core will actually tell us a lot about the history of the rock, what happened to the rock it was buried, how it retained its porosity and permeability, and if it happens to be a decent reservoir rock that we can use for CO2 injection. I'm not for sure if you guys are aware, but at the School of Energy Resources, we have very complex labs, some of the best in the world right now for studying flow through porous media. So we're very lucky to be able to do some high-level experiments that will tell us a lot about the reaction of reservoir rocks and seals to CO2 injection. The second thing that we're going to spend a lot of time trying to validate is the groundwater systems in the region. Those are the deep groundwater systems. And there's just not a lot of data from some of these formations. So we do have some data that's analogous and co-produced with oil and gas in the region, but some of the reservoirs have never been sampled for their water quality. So this will really greatly increase our knowledge of these systems with respect to the potential risk and how the systems evolve through time. The third piece of subsurface data we'll spend a lot of time with are petrophysical well logs. With respect to subsurface data, this is the largest available volume of data to any geologist, the subsurface well logs. So we will pull a whole suite of well logs from this core to teach us all we can about the porosity and permeability, the pore space of those pores, the seal types, the water types, the lateral continuity, and all of these will be used again to further expand our understanding of the geology that we're hoping to target and better formalize and validate for potential CO2 storage. And we'll also start to analyze those risks that Scott mentioned, specifically the geomechanical risks. So we'll get a lot of data, luckily, from the core, as well as the petrophysical data that will tell us how these rocks will react and can react to stress and pressure changes associated with CO2 storage injection, water production, et cetera. So what this will give us is kind of our safety box. We'll have our parameters, our lower highs that we know we can't go past. Now all these data go towards feeding our models. And our models, besides for the experiments and analytics that we do on the core and some of the water, these are true experimental playgrounds. So once we build these very complex geologic models using all the heterogeneity inherent in the geology at the site, which we couldn't just get from guessing, we have to actually drill a well. Once we build these models, then we can start designing experiments related to CO2 injection and storage. And this is one of the true up-proofs of validating geologic CO2 storage. It's design these very complex geologic models and then test them under varying parameters. So lastly, what's interesting about this CarbonSAFE project, it's not just about the geology. We also have to kind of take a holistic look of how it impacts region and other systems. So we'll also be taking an in-depth look and modeling stuff like the economics of utilization and storage, the permitting needs associated with CO2 sequestration in Wyoming, the different technologies and strategies we might deploy for a long-term monitoring system at the site, different risk assessments, We will continue to do community outreach much like tonight, and then we'll also build in all of this data to a statewide carbon management program. Now lastly, this has been brought up by both Kip and Scott. We see many advantages of doing CCUS in Wyoming. Here's a brief list here, but we believe all the key pieces are in place to do this not only the right way with respect to geologic storage, risk, and seals, but also all the regulatory and social pieces as well. So with that, I kind of rushed to get done, but thank you very much. Sir, so the question is, we're going to drill a very deep well, and then we're going to plug it before we have a chance to stick CO2 down to see if it'll work. So the answer for this phase is actually yes. So the question is, why would we not leave that test well open for future geologic storage? And there's a couple questions. So one issue, we will actually, before we plug and abandon, we will do a study to see if it's feasible to maintain that well as is. So we will take a look at that. But right now, because of the limitations of the grant, which we're not for sure if we're going to move past a phase 2, we have to build it in so we P&A so nobody's liable for anything out there except for us.
So yeah, the short answer is we will evaluate it for reuse, but we need to make sure that budget is there in the grant to plug and abandon if needed.
And the other interesting thing is, so we're drilling a deep well in Wyoming, which has very interesting geologic attributes. So all the data that we make will be publicly available. We'll make sure it gets out for everybody to evaluate what we've learned as well.
There's
Another question? What's the expectation at CarbonSAFE phase 3 and 4 continued funding? How many projects is the question?
It'll probably go down from 6 to 3 in the next round, and 4 will probably be just one project. So you're on the winning team now. We got to keep winning.
In the back. So the question, with all the Minnelusa wells that are in Campbell County and across the northern Powder River Basin, can we not collect the data there as well? We absolutely have collected that data already. And it's taught us a lot about what the Minnelusa system is and how it reacts across the basin. But geology, is very heterogeneic. So this, especially with the focus of trying to understand certain things, not just is there oil saturation in the Minnelusa, which is a typical reason these wells were drilled. Some of the science we'll deploy downhole will help us learn a lot more.
Can I answer?
Yeah, please.
So typically the Minnelusa wells in the Powder River Basin are drilled to the east of where we are. So we can learn a lot from those wells. They're typically completed in what's called the A sand. So at our study site, we'll be looking at sands below that A sand, so the B sand, C sand, and D sand, and nobody's drilled those yet. So we'll be adding a lot to what we know about the Minnelusa bottom strata.
It's a good point. And the reason they only drill the A sand because that's where the oil is. There's typically no oil below that. So.
For first grade question, but these places where we're going to be storing the CO2 are not linked to oil other than being in the same strata. Is that right? It's full of water where you're drilling?
We'll be targeting areas that we think are full of water. So if we go back just a few, apologize here, bear with me. And the question is, again, I didn't repeat it, sorry Gene, is the places we're drilling, are they associated with water, not oil? So these are some of the wells that were drilled around our project area, and most of them are quote unquote dry holes. So there was some oil shows there, but not enough to be economic. And the major target for us, as Scott mentioned, is the lower portion of the Minnelusa, which as far as we know only holds salty water. So the question is, does the CO2 dissolve in the water, or is the water displaced? The answer is the water is absolutely displaced. There is some dissolution, but you can imagine, so pore space in the subsurface is non-massive caves with geodes like in the movies. It's very small. I should have brought samples. And it's already full of a liquid of some sort, typically water. Generally across the world, 80% of pore space in the subsurface is filled with water. The other 20% is hydrocarbon. So if we stick CO2 into the subsurface with water-filled pore space, we will displace that water. And that's actually one of the places that the University of Wyoming forged ahead and cut its teeth and created a name for itself 10 years ago in the CCUS community, because we had a depth of understanding thanks to all the oil and gas we've done. So the very first early worldwide CCUS models didn't take pressure management into account. And Wyoming started that research 10 years ago. So that's very much part of this program, is pressure management with respect to displaced brine. So the question is, with the current unconventional production in the southern Powder River Basin, which actually targets some of these seals because they're organic and they hold hydrocarbons, how would this project impact those seals? Is that the question?
What does the hydrologic fracturing of, say, the Bowery to remove oil do to that seal permeability? Is it compromised? Seal integrity.
Oh, well, when they do the horizontal or hydrofrac, absolutely what they're trying to do is increase the permeability within that unit. So previously there's next to no permeability in those really tight units. So what they go in and they drill and they create artificial permeability by breaking the rock, and that goes through. We won't do that with this project.
But I think what you're asking is, what if we put CO2 down there and somebody else comes in and fracks the Mowry? What's that going to do to our project? That's a great question. So we would need to know that. Is this going to be a Mowry development area before we would put CO2 under it? And we will look at the total organic carbon in the Mowry as part of our seal analysis for this project. Now, if you look at the bottom, we've got another super seal. It starts with that Opeechee Formation up through the Gypsum Springs. That is not hydrocarbon bearing. So the seal directly on top of the Menalusa would never be explored for hydrocarbon. But you're absolutely right. We need to, in Niobrara and Mowry production, we need to be very careful there.
Can I also answer that too? There's also a legal answer to that, and that under those Wyoming statutes, they've already built into the law the competition between production and storage. So the Oil and Gas Conservation Commission would have to assess all of those issues. And the way the statute reads is that oil and gas production dominates over the storage, the state. So this future project for storage cannot, in theory, under the law, interfere with future energy production. But that, if that competition came up in the year 2100, we'll have to look at that in a thoughtful way under the law.
Okay. Thank you, everybody.